Only 14 kilometers of water separate Europe from Africa. At first glance, that sounds almost absurdly easy. Humans have already built tunnels beneath seas and bridges stretching for dozens of kilometers, so this should be one of the simplest crossings on Earth. But in reality, the Strait of Gibraltar is one of the hardest places on the planet to build anything permanent. Here, two massive bodies of water collide, creating underwater forces powerful enough to tear apart multi-ton concrete supports. To build a bridge here, engineers would have to conquer depths of up to 900 meters. That is roughly 3 Eiffel Towers stacked on top of one another. Add to that violent currents that constantly hammer any structure with enormous force. This is why, despite centuries of ideas and decades of serious planning, even the best engineers in the world still cannot solve these 14 kilometers of water. And the deeper scientists studied the seabed, the worse the problem became. Stand on the Spanish coast near Tarifa, and on a clear day you can see the white buildings of Tangier in Morocco. It looks close enough to touch. That illusion has fooled more than one generation of planners. While the crossing seems short, the reality on the ground is very different. In the port of Algeciras, truck drivers often spend days waiting for ferries. African vegetables and European electronics pile up at the edge of the sea, turning a short distance into a costly logistical bottleneck. Every hour of delay burns fuel, wastes money, and slows trade between two continents. A direct bridge would seem like a perfect solution. That dream is not new. Engineers were already imagining a crossing here centuries ago. By the 20th century, Spain and Morocco had moved beyond fantasy and begun serious studies. Research vessels were sent out, seabed tests were carried out, routes were drawn on maps, and governments explored the possibility of a real project. But as soon as drilling and measurement began, confidence gave way to alarm. Equipment failed. Test results came back with numbers that did not match normal engineering expectations. The problem was not simply money. Investors have long been willing to fund ambitious megaprojects. The real issue is that no architect or engineer has ever been willing to sign off on a final design. The first major obstacle is the water itself. The Strait of Gibraltar is not just a narrow channel. It is a collision zone between the Atlantic Ocean and the Mediterranean Sea. The cold Atlantic water is lighter, while the Mediterranean water is warmer, saltier, and denser. Because of that difference, the two bodies of water do not simply mix. The heavy Mediterranean water flows outward along the bottom, while lighter Atlantic water moves inward above it. That means the upper layer of water can race in one direction while the lower layer moves the exact opposite way at the same time. For a bridge support, that is a nightmare. Imagine lowering a giant pillar into the water and having its upper half pulled one way while its lower half is dragged the other. It would be like two invisible hands trying to twist and tear the structure apart every second. Current speeds here can reach around 4 meters per second, which is enormous for water of this scale. The pressure on any vertical support would be brutal. Even if the concrete did not fail immediately, the repeated force would slowly destroy it, and the surface currents are only the beginning. Gibraltar also contains something even more dangerous: internal waves. These are giant underwater waves formed at the boundary between the two water layers. On the surface, the sea may appear calm. But hundreds of meters below, massive waves more than 100 meters high can roll through the strait carrying extraordinary energy. When one of those underwater waves strikes a bridge support, the force can be comparable to a multi-ton train hitting at full speed. These waves are not only powerful, they are also difficult to predict. Instruments placed in the strait have often come back damaged, or disappeared entirely. Seabed scans have revealed grooves carved by currents strong enough to move enormous boulders as if they were gravel. Even that would not be the end of the story. The seabed itself is another disaster. Beneath the Strait of Gibraltar lies not a nice flat platform for foundations, but a giant underwater canyon with steep slopes, sharp ridges, and extreme depth. At its deepest, the strait reaches around 900 meters. Even the shallowest realistic construction zones are still far deeper than the sites where famous long-span bridges were built elsewhere in the world. Engineers sometimes compare difficult bridge projects to Japan's Akashi Kaikyo Bridge, but the comparison falls apart quickly. The sea beneath Akashi's towers is far shallower. Gibraltar is operating on an entirely different scale. That depth creates the next dead end: supports. A normal bridge needs huge concrete columns standing on solid ground. But here, no existing technology can reliably place and secure such columns at hundreds of meters deep under violent current pressure. It is not just a matter of dropping a pillar into the sea. It would need to be aligned with extreme precision and fixed to a stable base. A tiny deviation could lead to structural failure under its own immense weight. Then comes the question of what that base would even be made of. Studies have shown that much of the seabed is covered in unstable sediment layers. Instead of hard, reliable rock, engineers found loose deposits, soft material, and strange geological structures that behave more like a shifting mass than a foundation. Building here would be like trying to place a skyscraper on top of a giant mattress filled with wet sand. So engineers looked for alternatives. If a traditional support bridge could not work, maybe a floating bridge could. That idea sounded promising at first. A series of giant pontoons could support the roadway without needing to anchor heavy towers to the deep seabed. But Gibraltar is one of the busiest shipping lanes in the world. Every year, huge tankers and cargo vessels pass through this narrow corridor. A floating bridge would become a physical barrier to that traffic. One navigation mistake or one engine failure on a vessel weighing hundreds of thousands of tons could turn the crossing into twisted wreckage in seconds. And the floating structure would still need to be anchored somehow, with enormous cables under constant unpredictable load. Another proposal imagined a suspension bridge with record-breaking spans of around 5 kilometers. But that quickly ran into the limits of the materials themselves. The towers would need to be extraordinarily high, and the cables would be so heavy that they could begin to fail under their own weight. At that point, the bridge stops being a question of bold design and becomes a question of physical limits. So attention shifted to the tunnel option. If a bridge above the water is impossible, perhaps a tunnel beneath it could work. That would eliminate the problem of storms and ship traffic. But Gibraltar is not like the English Channel, where more uniform geology allowed a tunnel to be built through relatively predictable material. Here, the rock and sediment composition changes constantly. A tunnel boring machine costing hundreds of millions of dollars could end up trapped in unpredictable mixed geology. What looks like a solid engineering solution on paper begins to collapse again in contact with real conditions. And then came the most disturbing realization of all. The Strait of Gibraltar is not just a water problem or a depth problem. It is also a tectonic problem. This crossing sits near the boundary between the African and Eurasian plates. Africa is still moving slowly northward toward Europe. The movement is only a few millimeters each year, but for a rigid bridge that is terrifying. A structure fixed between two shores that are slowly pushing toward each other is already under long-term geological stress. Add earthquakes, and the danger grows even worse. The region is seismically active, and history shows that serious earthquakes have struck this area before. A conventional rigid bridge would be exposed not only to constant ocean pressure, but also to seismic movement from the Earth itself. Even if engineers could somehow solve the water, the depth, the shipping traffic, and the tectonic pressure, the final obstacle lies in the ground below. Detailed scans and drilling revealed that beneath the strait is an enormous thickness of unstable clay and soft sediment extending hundreds of meters down. Under high pressure and constant vibration, this material can behave almost like a liquid. That makes piling supports into it effectively meaningless. Any huge structure placed on top of it would simply keep sinking. Why is the seabed here so unstable? The answer goes back millions of years. Around 6 million years ago, the Mediterranean Sea nearly dried out. Then, when a natural barrier in the Gibraltar region collapsed, Atlantic water rushed back in during a catastrophic reflooding event. That ancient megaflood ground rock into fine sediment and deposited enormous amounts of unstable material precisely in this narrow zone. In other words, the very geological history of Gibraltar created the seabed that now defeats modern engineering. That is why the scientific verdict is so harsh. With current technology, a classic bridge between Europe and Africa at Gibraltar is not just difficult. It is physically unrealistic. The problem is no longer simply cost, design, or political will. The problem is that nature has stacked too many limits in one place: violent currents, internal waves, extreme depth, unstable geology, heavy shipping traffic, tectonic compression, earthquakes, and a seabed that cannot reliably hold foundations. Humanity has learned to build stronger materials and more ambitious structures than ever before. But we still cannot rewrite the geology of an entire strait. And here, that geology wins. The dream of connecting Europe and Africa with a bridge remains one of the boldest infrastructure fantasies in history, not because people lacked imagination, but because the Earth itself refuses to cooperate. Gibraltar remains a place where nature sets the rules and reminds humanity of its limits. And that may be exactly what makes it so fascinating.